Screen is visible?
Yeah.
Yeah. Thanks a lot. And that was an excellent. In fact, I'm very grateful to for you for that introduction. And as you rightly said, that we go long back, and we have been friends, especially in this in this cause of sustainability as well as latest ultra high performance concrete. Also, like we have been discussing and working together. Coming back to this today's topic, it is I've chosen a topic that's a decarbonization of the steel bridges, particularly the steel bridges. Before that, I would like to give some sort of a like background to that. What is this decarbonization all about? Why we are talking about the decarbonization suddenly, and how it is related to the climate change. And after having given a proper background to that, I'll just come to this subject of the particularly steel structure, steel bridges, how to decarbonize, by what time this decarbonization can take place. That is a whole presentation is all about. In fact, some of the slides I have taken from Dr. Harshavardhan Subbarao also, who had made a presentation in recently held with World Steel Conference, like in Delhi, all of us were participant, and there also Dr. Good to see Professor Siddharth Ghosh was also there in that particular international conference. Now, all of us know by this time, including perhaps Mr. Trump, that the climate change is not a myth anymore. Like that's a reality, and it has come to plague us, even in India, quite often by way of cyclones, by way of avalanches, by way of floods, and the precipitation patterns, which is not normal, basically in the abnormal precipitation patterns. And in over the period, especially after the pre-industrial era, the carbon dioxide concentration, started increasing. It has increased by 410 ppm, and alarmingly, in last decade, at the rate of 2.5 ppm, it has been increasing. Before that, it was increasing only by 1 ppm per year. That means this concentration of the carbon dioxide in the environment, I'm just going to explain that later. Actually, what is doing it? It's increasing it is what they call it as a global warming. All of you are aware of it. This global warming, if it is more than 1.5 degree by say 2050, I think perhaps this world will not be there. Like the 3 degrees, suppose if it goes to the 3 degrees and all, we can safely say there will be apocalypse on the basis of the manifestations of this climate change, which is taking all over the world in the form of precipitation patterns, floods, droughts, wildfires, landslides, melting of ice glaciers, as well as the avalanches, as you can see here. So all of us have to get geared up to that, and how to overcome this problem of, like this carbonization, which is leading to the global warming, thereby this disastrous manifestations. How to avoid that? We'll have to work on that. Now, let's have a look at this carbon dioxide emission to the environment. I think the data is varying across the world. Like the different sources give the different data. We are particularly concerned about the construction sector, basically, right? In the construction sector, it is said, it's all, like if you collect the data all over the world from the different sources, and again, if you average it out, what we find is around 12.75% is can be attributed to this construction sector, out of which cement is contributing around 3%, and the steel is also around, say, 2.75% to 3%, and other building materials is 1.25%, and utility, end of the life, beyond the life, around 5.75%. In addition to that, energy used in the buildings for the operation, like for the water supply, for the vertical lift movement, so many things, energy is required for the operation of the building. That is, contributing to the carbon footprint of, when we say carbon footprint, it's the carbon emission to the environment, basically, of 17.5%. So that is how it is happening. And in the world, India is responsible for emitting around almost in the rank third in the world. If you really look at on the right hand side of that, the China ranks first, and the United States ranks second, and India comes with the 6.6% is overall carbon dioxide emission to the environment. You can have a look at it. Though, but per capita, the carbon dioxide emission as well as the energy consumption in India as well as the China perhaps is lower, compared to that of the United States, because our population is very high. So if you look at the per capita, it may not be very high, but if you look at the absolute of the gross carbon dioxide emission, India ranks at around third in the world. I think it's a matter of concern for us. Now, because of this, whole world leaders and the whole thought leaders gathered together. I think it was first in Paris, what it called as a COP 21, and the world leaders committed to reduce the carbon dioxide emission or make it zero by 2015, the COP 21. And the Indian commitment was, as you can see here, some of the commitments were there. But that commitments, which was made in COP 21, was revised in the next meeting which took place in 2021 in Glasgow, that is called as a COP 26, where our Prime Minister very famously gave the Panchamrita, like what they call it as a Panchamrita, that means 5 panaceas to carbon neutrality, to achieve the carbon neutrality by 2070. And those 5 panaceas are here, like reduce economy's carbon intensity down by 45%, and he proposed in 2 phases. In fact, by 45% up to the first phase, that is by 2030, and the next complete carbon neutrality by 2070. This is for overall from the Indian perspective. It's not only meant for the construction sector, basically, it's for all. But very interesting and very exciting for our Indian subcontinent is that whatever we had promised in Paris, that is in COP 21, we could achieve quite a lot of, we could make progress in the carbon neutrality, achievement of the carbon neutrality, quite a lot. And we ranked among 10 top countries in the world. I think that's a credit. And India is in the right path, and in the right path of achieving the carbon neutrality as promised by, as committed by our Prime Minister by 2017. Now let me give the background, because straight away, before getting straight away into the how to like decarbonize steel bridges, let us understand what is this, what we are talking about, carbon emission. What does it mean? There are 2 types of carbon. One is called the operation carbon, and another is called the embodied carbon. We'll have to understand. Carbon emission or the global warming potential always has been expressed in terms of a kg carbon dioxide equivalent or a ton carbon dioxide equivalent. That means, like the greenhouse gases, carbon dioxide, along with the carbon dioxide, there are other greenhouse gases like CH4 and NTO, etc. But maximum or the majority of this greenhouse gas emission, carbon dioxide accounts for almost around 90 to 95%. So most of us will be concentrating on the carbon dioxide emission rather than CH4 as well as the NTO. That is why we call the emission which has been taking place into the environment, which can cause the global warming. So 1 kg carbon dioxide emission to the environment causes the global warming, has the global warming potential of 1 kg carbon dioxide equivalent. That we'll have to understand. Now, there are, as I told you, there are 2 types of carbon. One is the operation carbon, another is the embodied carbon. Operation carbon encompasses carbon dioxide emission. I'll be talking about the carbon dioxide emission. That is always equivalent to that of greenhouse gas emission. You have to understand that. Energy centric operations in buildings such as heating, cooling, and ventilation and lighting system. These are called the operation carbons. Whatever the lighting system we have in the buildings, and that is called the operation carbon. And this operation carbon normally, which is used for the purpose of the energy, which is used for the purpose of operations of the buildings like heating, cooling, and ventilation and lighting systems, etc. This is the energy which is supplied directly. That energy only way to reduce this operational carbon is but to go for the renewable energy sources. Normally, whatever the energy we are getting and we are spending right now is from the non-renewable fossilized fuels like the coal, natural gas, and petrol, and particularly coal burning. The thermal power plants which has been producing energies in our country normally use the coal, and by coal burning you produce the energy, and that energy is used for the operational purpose, that is called the operational carbon. So one way of reducing this operational carbon is to replace this non-renewable energy sources into the renewable energy sources like wind energy, solar energy, hydroelectric energy, biomass energy, as well as the nuclear energy. And the extensive research has been going on all over the world, and the debate is going on. In particularly, this energy sector is quite ahead in addressing this carbon neutrality issue all over the world, in my opinion. And there's a lot of debate going on whether how the nuclear energy can be made cheaper compared to that of whatever the energy is being produced by the thermal power plants these days, and how the solar energy and wind energy, all these energies are, little bit, like expensive compared to that of the fossilized fuel, non-renewable energy, which has been produced right now. But the research is going on as to how to make it economical. A lot of work is being done. The embodied carbon is the carbon emissions associated with the 5 main stages of the structures. Basically, we'll have to understand product stage, construction stage, utility stage, quantities. You will get what is the kg carbon dioxide equivalent, which is reduced, which is emitted to the environment. That is the embodied carbon. In most of my presentation today, when you are talking about the decarbonization of steel bridges, I'll be most of the time concentrating on this embodied carbon, because embodied carbon, 50% of the embodied carbon emission takes place at the product stage itself. When you say at the product stage itself, manufacturing of the steel itself, manufacturing about the cement itself in case of the concrete. That if you can somehow control that embodied carbon during the product stage as well as the construction stage, will be able to control or will be able to achieve the carbon neutrality by 2070 as committed by our Prime Minister, and that is our aim when we are talking about the decarbonization of the steel structures or for that matter the construction industry itself. So what is the carbon neutrality? Now we have all committed to achieve the carbon neutrality by 2070. Let us understand the concept of, I have tried to give here a model of my own here. On the right side, you can see here, it is the estimate, avoid, reduce, and set up, what I call it as. I call it as in years, like EARS, and that is a kind of model. Carbon neutrality is a process where carbon dioxide emissions are brought down to this net zero by avoiding and reducing, where avoiding and reducing is not possible by setting off. That is the process is carbon neutrality achievement. Basically, that's how we do it. First of all, we'll have to calculate. Actually, if you really look at when I say the estimate, we'll have to calculate what is the embodied carbon and what is the operational carbon. That calculation has to be done. Unfortunately, in India, that calculation process is still, has to take place, and there is not agreed or consensus, embodied carbon coefficient or embodied carbon factors, which is there, that the estimation has to be still done. A lot of work is going on. People are working on that. We'll have to do that. Then once you estimate it and avoid those sort of activities which emits the carbon dioxide to the environment, that is the avoid. But you know that the construction material like concrete as well as the steel is a necessary evil. We cannot completely avoid that. And when it is not possible to avoid that, what we have to do is, how do we reduce this carbon dioxide emission using the same concrete, using the steel? That's what we'll have to work out in the third phase of it. When it is not possible for us to really avoid it and reduce it, as I told you earlier, it's not possible to avoid the concrete construction or the steel construction. It's a necessary evil. For the infrastructure is very much essential for us, and it's a basic building material for us. Avoiding and reducing to a certain extent, we'll be discussing the strategies of the reduction later, but the avoiding is totally cannot be avoided. So which cannot be avoided, we'll have to set off, like those carbon dioxide emissions has to be set off. That is what is called as a whole package of this, or the model is called the carbon neutral model, as you can see over here. There are a lot of standardization in the world. ISO has its standardizations, and there are Euro codes, basically, as you can see on the screen over here, for the sustainability of construction work, assessment of the buildings as well as the civil engineering works. EN 15643 is there, and there is a general framework. Also, there are guidelines, for the framework for environmental performance, social performance, as well as the economic performance, how to calculate, basically the calculation methods for the environmental performance. When you say the environmental performance, global warming potential performance, basically. And there is also calculation method is given in EN 16309 for social performance, and also for the life cycle costing or the life cycle assessment for the economic performance. The calculation method is given in EN 16627, as you can see here. And also ISO as well as EN 15804 has come out with core rules for the product category, especially the under environmental performance criteria. These core rules for the product category is called environmental product declarations. I think that's very, very important. On the basis of the environmental product declaration, that the green certification, etc., normally takes place. I think that is how it is there. So the standardization is very much there, and this standardization has come out long back. If you really have a look at it, 2010, 2011, 2012, 2015. So it's been it's a work in progress. The people have been working all over the globe on the standardization of the sustainability since quite some time, with which from the Indian subcontinent we'll have to really catch up with. Also, you see, it can be divided into 4 categories. Actually, this carbonization, especially when you do the life cycle assessment for the economic assessment as well as the carbon assessment, we have to do it at the product stage. These are some of the boundaries which has been decided over here. Product stage has been represented by A1 to A3. Basically, raw material supply, transport, manufacturing. In case of the steel, how steel is manufactured. In case of the concrete, how the concrete is manufactured. I'm talking about concrete as well as steel because it's the major carbon emitting building material which has been used now all over the world, not only in the world, even in India for that matter. Then the construction process, as you can see here, it is represented by the boundaries A4 and A5. Then U stage is there, end of the life stage is there, and finally the D stage is reuse, recovery, recycling potential has been calculated on this. Now, I also explained environmental product declarations, and that core rules has been, when it is applied up to this, only the construction or the product stage, it is called the EPD cradle to gate. When it is applied from product stage up to the end of the life stage, or even for the matter, reuse and recycle stage, it is called the cradle to grave. That means the product material has been produced and it has gone to its grave, and up to that, both this like environment product declarations as well as the assessment of the economic assessment and the social assessment and the environmental assessment, global warming potential assessment, all this can be done for all these boundaries which has been defined. And there is a code that is a CE, that the guideline is CEN TC 350 that has been available, and it has been extensively used by most of the researchers for doing the research in sustainability aspect. In fact, the same thing I have converted for a cradle to construction. That is only the product as well as the construction stage. On the screen, if you can really look at it, I've taken the 2 major building materials. On the left hand side, cradle to construction, the concrete model, and when the concrete is being produced in the raw material stage, up to the production, placement, transportation, as well as the placement, how the carbon dioxide emission takes place, how much energy is required for that. That energy again, like when producing that energy, again carbon dioxide emission takes place. All this combined together, ultimately we can call it as a carbon footprint. And similarly, in the case of the steel structures, basically the steel structure manufacturing, and then it has to be transported to the yard. Fabrication has to take place. Different processes has been shown on the screen, if you can see here. Finally, after transportation, that's fabricated material has to be transported to the site, and we do the erection. The entire process, the construction product state to the construction stage, the carbon dioxide emission takes place. Also, the cost incurred. So the assessment at that stage for both the environmental assessment as well as the global warming potential assessment as well as the economical assessment can be made for both these stages. So we will be basically concentrating on the right-hand side model, that is for related to the steel bridges when we come to that. Now coming to this steel bridges, like that, let us understand how much carbon dioxide emission is taking place because of the steel bridges. I think I've given here a table you can see here. And in India, for the financial 21-22, if you really look at it, 120 million tons steel has been produced. Out of this 120 million steel which has been produced, 106 million tons steel has been used. Out of this 106 million tons of steel which has been used, around 29 million tons is been used in the infrastructure, especially coming to our topic today, 9 million ton structural steel is used in the financial year 21-22 in India. The 9 million ton structural steel which has been used for the bridges emits around 63 million ton carbon dioxide equivalent, basically 63 million ton carbon dioxide equivalent. And if you really look at it, you have a look at here, actually what I have done, you see, if you, for carbon emission, for producing 1 ton of steel, normally on an average 2 ton carbon dioxide equivalent is being emitted. For producing 1 ton of steel, 18 gigajoule, the energy is required. In fact, it is a very lesser side I have taken, that the energy required for production of the steel is much more than that in some cases. I think the variance are the variance, it is been range is quite a lot. In fact, it is ranging from 18 to even 30 gigajoule. But for the purpose of the calculations, on a lenient side, I have taken 18 gigajoule per ton. And that energy, if you really look at it, producing 1 gigajoule of the energy, we require 1 gigajoule of energy. While producing 1 gigajoule of energy, 0.28 ton carbon dioxide emission takes place. That means for using around 18 gigajoule energy for production of the steel, basically we are emitting around 5 ton carbon dioxide equivalent by the energy consumption for the production of the steel. Whereas for the direct carbon dioxide emission, if you really look at it, is 2 ton carbon dioxide equivalent. The energy used for the production of the steel is 5 ton carbon dioxide equivalent. That means the 5 ton carbon dioxide equivalent energy, carbon dioxide equivalent takes place for using the 18 gigajoule gigajoule energy. So the energy used for the production of the steel is almost emitting around 70% of the carbon dioxide. That is the embodied carbon of the embodied energy of the steel manufacturing is around 70% of the overall embodied carbon content. That is a very interesting thing to note over here. And when I'm concluding, I think most of the emphasis by us has to be made how to replace that energy with the renewable energy resources. That is what is very important as far as the steel is concerned, if you want to make the steel the carbon efficient going forward. Now I'll come to what are the strategies to achieve the carbon neutrality in the bridge construction. You see, I explained to you in Paris, that is in COP21 meeting, the agreement which has been done. If you take that the carbon dioxide emission of the global warming potential is 120% by 2021, when we had a meeting in Glasgow, that is the COP26, where all the world leaders had gathered, we had almost reduced this carbon dioxide emission by around 20%, like 120%, say for example. I'm just making this 2021 as a reference point where the 100% carbon dioxide emission is taking place, especially in the bridges, structural steel bridges, if we take it. How we can bring it down to this, in case of the structural steel, the carbon neutrality, how can we achieve by 2017? And there could be 6 strategies, as you can see here, which has been noted over here. One is by the design efficiency, saving the carbon dioxide emission through the design efficiency. Second is the circular economy. I'm going to talk about it a bit. And third is the reduction at the production stage itself. Direct emission of the carbon dioxide is taking place while producing the steel. That is around 2 ton carbon dioxide equivalent is getting emitted for producing 1 ton of the steel. That has to be reduced. And also decarbonizing energy. In the sense, we know that energy required to produce 1 ton of steel is 18 gigajoule. If you take on a lenient side, that means around 5 ton carbon dioxide equivalent is taking place for using that energy, because this energy is coming from the non-renewable resources, fossilized resources basically. So that is emitting the energy when the energy is the carbon dioxide into the environment, when the energy is being emitted to the used for the production of the steel. So that we'll have to see how do we replace that with the renewable energy sources basically. Then we come to the another strategy of basically carbon capture, use, as well as the storage. This carbon which has been emitted during the process of manufacturing of the steel itself, not only for manufacturing, even during the operation also, in somehow, if it's possible for us to capture it and convert into some other chemical or convert some other product which can be used in some other industry. That's how a lot of research is going on. That is also one of the ways of really reducing the carbon dioxide emission to the environment. Of course, in case of the steel, during the transportation, fabrication, as well as the erection, mainly the carbon dioxide emission is related to the embodied energy. I think around 8% embodied energy requirement is there for fabrication, transportation, as well as the erection. That is what my rough estimate is. And again, we'll have to have ways and means to replace that fossilized energy which we are using right now with the non-fossilized energy or a renewable energy. That's how we'll have to go about. So it's possible for us roughly. I think it's not a well-researched data, but it's on the basis of calibrated data, which has where the work has been done on other countries. This is my personal assessment. It's possible for us to save, in case of the bridges, steel bridges, especially the 17% by the design efficiency, 15% by the circular economy, 28% by the reduction at the product stage itself, 7% by the decarbonizing energy, and 25% by CCUS and transport and fabrication erection by 8%. By doing that over the period up to 2070, it's possible for us to achieve design efficiency is in our hand, construction processes including the production and erection is in our hand, and to a certain extent circular economy is in our hand. Basically whatever comes out of this, and if it can be recycled, reused, and that it can be widened later, and those are methods, the circular economy these are the 3 things we are in which our hand. Only 30% carbon neutrality achievement in
recording in progress.
Basically that slag has to be used as much as possible. In fact, in the concrete itself, up to 85% that slag can be used. And there are slag aggregates also. Basically, that can be used. Recycling glass residue as lightweight aggregate, replacement of OPC with mineral admixtures like slag. I said slag is an industrial byproduct of steel making. Going for the HPC, HSC, high-grade steel for enhanced sustainability, self-compacting concrete, UHPC along with HTS, design-build concrete type. In the design-build contract type, it is possible for us to do the value engineering as well as the carbon engineer in the next slides. And very, very importantly, the role of the owners as well as the architects who have been preparing this DPR for that matter, architects and the other engineers have to specify the limits for the carbon dioxide emissions and the energy consumption in the contract itself. if this with the stringent penalty clauses for exceeding the same, and also high rating, that the QCBC methods which has been used for the contracting, the procurement has to have the carbon footprint as one of the major criteria. A lot of emphasis has to be given on that. That is how the owners as well as the architects and the detailed design, the DPR consultants, and also the contract formulators have to really, they've got a lot of things to do as far as this is concerned. Now, as I told you that you see in a concrete construction, if you want to achieve the carbon neutrality, one of the ways of achieving the carbon neutrality is replacing the cement by the mineral admixtures. I said that, like the cement in a concrete, 1 cubic meter of concrete, if you really look at it, cement contributes to 90% of the carbon dioxide emission. Basically, the carbon in the environment, as you can see here, by way of replacing this OPC, that the ordinary Portland cement, with mineral admixtures like fly ash as well as the slag. And the slag is the industrial byproduct. Why I'm talking about the slag here is slag is an industrial byproduct of the steel making. We are talking about the steel decarbonization over here, and it's possible to replace the OPC in the concrete by around 85% in the world, even up to the 85% in the world. It has been replaced. I think also nowadays we are allowing, even in the IS 383, the use of slag aggregates. I think it's been permitted only 10% replacement of the natural aggregates. I think we should allow up to the 30 to 40% of the slag aggregate, and also slag has to be processed in the plant itself in such a way that it can be used in the concrete production. So only thing is the debate is going on for the carbon credit for this. I know, like use of slag, whether it has to be given to the steel industry or to the concrete industry, the debate is on. But I think it's a byproduct of the steel. I think perhaps it's better to give the credit, in my opinion, to steel manufacturers over here. Another thing is the designer's responsibility by value engineering during the engineering as well as the design. Normally, any project for that matter, when you are creating a value, the value of a project is created at the design and the engineering stage itself up to the 70%. And there, when the value of during this design engineering itself, normally if the value engineering can be done, up to 10 to 15% saving is there, 15% of the 17% of the cost can be reduced. Similarly, this concept of value engineering at the design stage can be expanded to this, even the carbon carbon footprint reduction, also what I call it as a carbon value engineering. In fact, luckily for us in the construction industry, when you make these structures economical by use of the value engineering, by adoption of the value engineering, automatically the carbon value engineering also takes place, because the whole idea of value engineering is to reduce the mass of the product itself, mass of the building material itself in the project. If you are able to reduce the building material quantum itself in a particular project by value engineering, I think we'll be achieving the carbon footprint reduction to a large extent. This is one of the ways, and we'll have to emphasize on carbon value engineering going forward. It's not just value engineering for reducing the cost. That's very, very important in my opinion. Let us look at some of the sustainability characteristics of the steel bridges. There's a lot of myths as far as the steel structures are concerned. They feel that it is not durable structures. They feel that it is not an elegant looking structures. And also, sometimes it's all maintenance prone. It requires a lot of maintenance. And but the facts are, the statistics all over the world, not only in India, proves the other way around. If you really look at some of the bridges which has been lasting for a long time in India, the Abdul Bari bridge, this is a bridge opened in 1862. The steel bridge, I think it's a double-decker bridge, as you can see here. It's still serving the purpose. It's a railway bridge, of course. And then Old Naini Bridge, opened in 1865. It is still serving. More than 150 years, it has been going strong. I have not come across any pre-stressed concrete bridges which has been serving more than 100 years. Of course, pre-stressed concrete technology has not evolved. It's only evolved in last 60 to 70 years. It has not seen the test of, seen the uh, uh, test of its time. But still, if you really look at it, some of these bridges which has been lasting for a long time. Another bridge is Malavia Bridge. There are many bridges in Bihar as well as the UP, especially the railway bridges. In fact, it's a double decker bridge, as you can see here, multimodal transport bridge on a single same substructure as well as the foundation, as you can see here. Another is the Pamban Bridge in Tamil Nadu, opened in 1913. So some of the myths has been, like if you really look at it, those bridges are sort of exploded. That the myths the myths are myths only. They're lightweight structure, long lasting, easily maintainable, service inspectability is easier, rapid and efficient construction is enabled, ease of dismantling and reusing their materials is possible, reliability and redundancy is possible, reduced waste and pollution in case of the steel structure construction, long span construction. I think I'm going to show some of the slides. Quality and predictability is certain in case of the steel construction. So it has been long lasting and it's a highly sustainable characteristics these steel bridges have, if you really look at it, compared to that of its counterpart concrete bridges, if you really look at it. And also, see, some of the studies which has been done by Garg et al. Like he studied the bridge collapses during the construction, as you can see on the screen over here from 1977 to 2017. It is interesting to note, out of the studies which he has conducted, 86% of the bridges which collapsed during the constructions either were RC bridges or pre-stressed concrete bridges, whereas steel bridges only around 13%. In fact, was the steel bridges during the construction. That too because of the collapse of the scaffolding, basically. And it is not that there are not steel bridge failures during the construction, as you can see here down. This is a cantilever collapse when the concreting is going on, but the scaffolding collapse, particularly over here, this is because of the overloading at the right hand bottom. But it looks like from the statistic that the steel bridges are less prone to the accident during the construction compared to that of its counterpart RCC as well as the concrete bridges here. So it's less accident prone, which I can see here. Also, it enables long spans compared to that of RCC as well as the pre-stressed concrete by virtue of its high strength weight ratio and also the high ductility perhaps. Most of the categories, if you really look at it, world record holding bridges are in steel, steel as a building material in case of the bridges. This is a Canacle bridge, a 1915 bridge, which is called as Turkey. This is of 2023 meters span, record holding. Rescue bridge, it holds the record right now for the cable stay bridge. Quebec bridge at Canada, 549 meters. It's a cantilever bridge. Basically, its records holds the record for the cantilever, longest cantilever bridge. Arc bridge in China of 552 meters. And this is also holds the record for the arc bridges. This is not a composite arch. This is a steel, pure steel arc bridge, as you can see here. And also this, surprisingly, extrudos bridge, what all of us understand that extrudos bridges, that can be constructed using only the concrete, pre-stressed concrete particularly. If you really look at it, even for the extrudos bridge, the world record holding 312 meter long extrudos bridge, which is constructed in China, that is again holds the record. It's a double-decker extrudos bridge, as you can see here. And even for the hybrid bridge, when I said it's a hybrid bridge of the combination of the cable stay bridge as well as the suspension bridge of 1.408 meter span, again it is made up of steel. Again, this third phosphorus bridge is a road cum rail bridge in a different manner, in the sense roads as well as the rail traffic on side by side rather than on one top of the other. So if you really look at the world record holding bridges in any category for that matter, whether it's like suspension bridge, cable stay bridge, or the cantilever bridge, arc bridge, even the extrudos bridge, including the hybrid bridges, it is in the steel material has been used over there. One of the advantages of going for the long spans, especially in the creeks, seas, as well as the river, is it reduces the foundation. And the studies show that the foundations as well as the substructure in the rivers and the creeks are more highly carbon intensive. As such, not only highly carbon intensive, it's highly uneconomical also. As such, it's necessary to reduce the foundation. So the spanability or the ability to increase the span by using the steel structure reduces the foundation. As such, the carbon emission to the environment also gets reduced, and it helps in achieving the carbon neutrality. Another myth is the steel structures look ugly, like the trusses and those sort of things. It's possible to have wonderful bridges, elegantly looking bridges like Namaste signature bridge at Delhi. I christened it, or I named it as a National Namaste signature bridge because it has a, like a Namaste pose welcoming the onlookers on the bridge, and it is a signature bridge. It is in the national capital. That's why it can be called as National Namaste signature bridge, and it reflects the local culture as well as the tradition, and in its visual form. And also another bridge, Atal Bridge, which has been inaugurated by Mr. Modi recently in Ahmedabad. If you really look at it, the kite culture of the Ahmedabad, it's reflecting. Another bridge which is at the bottom left, the Deccan Footover Bridge in Pune, the Punite Pagadi, that this is Pune Peta, which they call it, reflects that. The third is that the Sambhaji Kanpur Footover Bridge again, which will come up in Pune again. It reflects the Tanpura, Bal Gandharva Hall is nearby to this, where Bal Gandharva used to sing and Tanpura used to be played along with his singing. That sort of cultural reflection is there. So the steel structure, steel bridges could be highly elegant and aesthetically pleasant. Something is there in the aesthetic as well as the elegance that always is associated with the sustainability. I'm not able to really pinpoint that what is that off factor which makes the aesthetically looking bridges more sustainable. I think it is some relationship is always there between the aesthetics as well as the sustainability, though it is not possible to really quantify that, in my opinion. As I told you, maybe that less accidents are taking place during the construction in case of the bridges, but it is not, though it is less, many accidents are taking place because there are not sufficiently trained designers in the market, and somehow like this academic institutions are not giving much importance to the design and construction of the steel structures, and that the number of credits in the engineering colleges are quite less. It is always the emphasis is given on the concrete structure. Perhaps there's a need for us to look into this the engineering subjects. The academia has to concentrate on that. Another aspect, as far as the concrete is concerned, even the concrete production is a concrete technology that has been well taught in the universities. But when it comes to steel, it involves the fabrication technology, and the steel is already prepared and given, and the composition of the steel, manufacturing technologies of the steel. I think perhaps the structural engineers also has to be taught with. Presently, the fabrication as well as the processing of the steel, manufacturing is only taught to this is to the mechanical engineers, if I'm not mistaken. Perhaps there's a need for us to strengthen the education in case of the steel designing, steel fabrication processes, as well as steel making itself. Like if it can be taught extensively in the engineering institutions, and also we can train professionally the steel designers. I think it will be going a long way in really stopping these accidents which has been taking place. Though it's not as much as in the concrete concrete bridges. Another aspect is the double-decker structural systems for the decarbonization. Whenever you are going for a long span bridges all over the world, especially the Chinese, if you really look at it, we have Bogeybill Bridge and also the Patna Bridge, which has been talked about while Dr. Harshavardhan Subbarao was being introduced, there are a number of double-decker bridges, in the sense multimodal rail as well as the highway are run on one single bridge, which is on the same foundations. I think it's a more sustainable way to go about it. I think the steel as a material enables it much better than concrete. I think from that point of view, it's a structural system for the double-decker system. In recent years, even the cable stay bridge, which is under the construction, that is Changtai across River Bridge, it's a double-decker bridge which allows rail traffic as well as the road traffic, and it's going to be 1176 meter, which is going to break the record of Rusky Bridge, which is under construction. Whatever the bridges which have been constructed in China these days, the long span bridges, most of them are double-decker. I think it makes sense. And for me, it is inexplicable that the Trans Harbour Bridge, like this Trans Harbour Bridge, which has been going on in Mumbai for almost 10 kilometers, it doesn't have a double-decker bridge. I think it would have been a very good idea to have a double-decker bridge. I'm sure it's a highway bridge right now, and after some time, the public policy makers will have to come out with another metro line over there. Whole work of the foundation has to be repeated. I think it's a policy makers also has to be, oriented towards the carbon neutrality. In nutshell, I would like to say that it gives the better option for the double-decker system for the bridges, this steel. I think from that point of view, it's a more sustainable construction material. In China, again, the arch form has been, especially the composite arch, in the sense the concrete-filled hollow section. These are, it's wrong, the arch bridge, which is holding record for the longest span arch bridge in China, in the world, in fact, of 575 meter. This kind of long span arches is made possible by use of these concrete-filled tubes, basically, that the high tensile steel tubes filled up with the high strength concrete, high performance concrete, which has been filled up, and the spanability is increasing. Going forward, I think it's not only 575 meter, now with the advent of this ultra high performance concrete, also the steel of the strength of 1000 MPa, perhaps the combination of these two will lead to the much higher span arch bridges, the CFT, the concrete filled hollow section tubes that I can see. So this kind of the structural system with the combination of the ultra high performance concrete as well as the ultra high tensile strength steels will give a lot of sustainable options for the steel bridges too. This is for the bridges, buildings. I'll just skip this slide. Even in the buildings, the composite columns, which has been extensively used in Japan, with the combination of 150 MPa ultra high performance concrete as well as 780 MPa high strength steel, and it's possible to increase the space inside, and the facade area is reduced, and so many advantages are there. Sustainable options is there, but I think it's in the buildings, it's not in the bridges, so I'll just skip. How this designers can save by the design efficiency by use of very high strength steel, concrete to reduce mass, different types of the steel, stainless steel, weathering steel, high strength steel, and the detailing category of the fatigue. Like if you're going for a welded connection detailing category, normally the section requirement is high. I think perhaps as far as possible, it is better to avoid the welded detailing categories, and it's better to go for the bolted detailing categories where the sections of the steel section can be reduced, and the standardization and modular construction for waste reduction and the fast construction can be used. Pre-stressing in steel bridges to reduce the quantum of the steel. I think it should be explored more and more going forward. The pre-stressing can not only be used for the concrete, can be also used for the steel trusses. I think going forward, we should use that options. Use of composite construction, I explained that. Design for future upgradation, widening as well as the reuse, optimizing the connection details, detailing for better sustainability as well as the durability, improved corrosion protection, adoption of the orthotropic floors for the decks and the pylon shells. When the pylon is made up of steel, even the shells of the pylon can be made with the orthotropic plates, as the orthotropic plates are found to be less quantity-wise requirement is less. The carbon efficiency by high strength steel is not a new phenomena. In fact, if you really look at it, I think if, I don't know whether Mr. Ghoshal Saab is there, it has been taken from his book, The Howrah Bridge, which was constructed in 1943 by using the high tensile steel, shifting over to high tensile steel from the original design of a normal steel of 250 MPa. It seems to have achieved 10,000 ton steel reduction, the reduction in the steel itself. Similarly, in the second Hooghly Bridge, 450 meters span, 57 meters span for the pylon, as well as the composite deck construction, the high tensile steel has been used. So the high tensile steel has been continuously used. Another option, especially in the coastal area, where if you want to use the durability of the concrete, I think perhaps it is better to go for the stainless steel. One of the example of the foot over bridge you can see here, which has been done in Visakhapatnam. I think the MORTH is coming up with a policy to make use of stainless steel mandatory in the areas close to the sea. That seems to be a good option from the carbon footprint reduction point of view, especially from the maintenance requirement is less, and from that point of view. But only thing we'll have to be watchful is for producing the stainless steel, I think the energy required right presently using the current state of the art, energy required is 50 to 60 gigajoule per the ton of production of the stainless steel. But unless this energy requirement energy is replaced with the renewable energy sources, I think it carbon intensive wise, I think it's not going to be carbon friendly product. Only from the maintenance point of view it may be, but unless this energy requirement is replaced with the renewable energy sources, it is going to be carbon intensive. The stainless is going to be carbon intensive. Other option is the weathering steel. I think if even by going to the weathering steel also, it's possible for us to really reduce the maintenance requirement, and normally the dense and sticky the layer forms, whether rust forms on the top of this kind of steel, and it will be taking some time for the formation of this steel. This rust resists the ion penetration into the steel and initiation of the corrosion process, and this bridges can be designed even up to, in my opinion, up to 150 to 200 years with the weathering steel, but the thickness, the rust thickness requirement may be more. Accordingly, it has to be designed. There are some examples which has been done in 1989 in Okuso Bridge, as you can see here, and also the Constance Cycle Bridge, which has been done. There are several examples. One of the examples in the initial stages, this rust formation may look, but over the period, like if it becomes a dark brown color, as you can see here in the right hand top corner of the slide over here. Another carbon efficiency technology is the modular bridges, which has been discussed in our B5 committee. I think it's good that the convener of the B5 committee, Mr. Puri, is among us today, and we will be able to bring out this also. It enables very fast construction, reduces the wastages, and when it enables the fast construction, normally the traffic congestion is reduced. Traffic congestion will not be there at that particular area. Traffic blockade will not be there for a long time. And in this particular cases, modular bridges, the panel bridges are faster modular bridges to assemble and simple to launch. Of panel length, and it can also be said to be the carbon efficient bridges. And there are patented. One is Acro, and there are several, many in fact. Also, the steel in the decks as well as the pylons, as I told you, can be reduced by going for the orthotropic plate system. As you can see here on the right side, in the transverse direction as well as the longitudinal direction, they will be having a different the properties. Basically, when you say the orthotropic plate, over here you can see here is a longitudinal girder. This is the cross girder, as well as again, there are several longitudinal girders over here. It's possible to reduce this, the weight of the steel. When the weight of the superstructure is reduced by turn, the foundation weight is also reduced, and it is possible to have the carbon efficient solution by use of this orthotropic plate solutions too. And in my opinion, most important thing is the role of the standards and the code makers in the decarbonization. In case of the steel bridges, I think particularly, I think it is B5 committee which comes into the picture, and they have been bringing good guidelines. That the tub girder guidelines is going to be approved by the council shortly, and there is a need for even the extrudos as well as the cable stay, especially the cable stay where I think the composite girder for the long composite deck for the long span cable stays invariably it is required, especially when you're going beyond 550 meter span. The cable stay bridges are normally economical, not only economical, even carbon efficient with the composite girder deck. In fact, beyond 700 meter, you will have to go for the orthotropic plate deck, which is steel, and on top of that, as I explained, you will have to have the wearing course, which is directly laid on top of the orthotropic plate, and that's how normally the work is done. And very important is the review of safety factors to make the structures less carbon embodied. The safety factors as well as the load factors, which has been used for the concrete, need not be used for the steel structures. Basically, if you really, what are the safety factors? When you talk about the load factor, it is possible in the concrete material as a material, the variation in the density is possible, variations in the imperfection, casting imperfection is possible. When you are using the steel structure, steel plates, the variation to that extent is not possible. So it's necessary for us to really look at these load factors, especially for the steel structure. And also it's not necessary when you're going for a very high kind of the steel, and when you go for the concept of the pre-stressing of the steel itself, not to specify the span to depth ratios in the steel structures, that will stifle, like the reduction of the quantum of the mass of the structure itself, which is carbon, which is one of the methodologies to achieve the carbon neutrality or the carbon efficiency. Allowing composite piles for the pile foundations. In the pile foundations, invariably, especially in the rivers, we use the liners. I think the liners can be made to be taken, the properties of the liners can be made to be taken into consideration in the design itself, final design itself. According the thickness of the liners can be explained, increased, and also we should allow the piles to be designed as a composite section. I think these are some of the methods, the roles, the standards and code makers can permit from the point of view of the carbon neutrality or the carbon efficiency. The codes and standards should catch up with the emerging new technologies and material science very fast for applications. Unfortunately, say for example, this tub girder and the cable stay and the extrudos guidelines, and also another ceiling which you are bringing it out, all these guidelines are taking too much time. And of course, we have done a lot of work to bring out this extrudos, cable stay, as well as tub girder, which is going to be out. But I think the way the research is going on, the technologies are emerging, and this has to be condensed in the codes and as well as the standards as early as possible from the point of view of the carbon efficiency going forward. And also there is some sort of the idiosyncrasy among we, including myself. I'll tell you that the workmanship in India is very poor. To take care of the workmanship, load factors have to be increased, and the factor of safety have to be increased. I think that is to go above, especially in view of this climate actions which has to be taken. We have to make sure the workmanship is ensured by providing the factor of safeties as well as the load factors. I think it's not possible to improve the workmanship at the site. I think if the people are not doing proper work, I think those people who are responsible for getting the work done properly, they have to get the work done properly. That is where the concentration has to be there, rather than having an idiosyncrasy. To cover up the workmanship, we'll have to increase the factor of safeties, which makes the structure carbon sensitive, in the sense carbon efficiency is lost by increasing the factor of safety, as well as it especially I have seen that happens during the codal committee meetings. Sometimes I think it may come even from me, but I think we'll have to get out of that idiosyncrasies. Then how do we reduce this carbon footprint during the transportation, fabrication, and erection? Only way I think is to replace the energy source. I think it's around, I consider it around 8% carbon emission takes place in the steel bridges when you are doing due to the transportation, fabrication, and erection. That is my study, but it may vary quite large depending upon the various studies. And that has to be reduced. That can only be done by use of, like this renewable energy, especially the biomass energy and the solar energy. I think wherever it is possible for us to have a solar energy as well as the biomass energy and the wind turbines and even the wind energy, it's possible to get those energy sources to replace the non-renewable energy sources which is being presently used. I think that's the only way to reduce the carbon footprint during the transportation, fabrication, and erection. It's not possible. And also some of the carbon efficient fabrication technologies by use of digital technologies can be used, and renewable energy, I said, LED lighting can be used, reduction in compressed air leak and gas systems can be made, power optimization, use of inverters, new generation well set, hybrid and electric company vehicles for the transportation of the materials inside the casting yard, the fabrication yard itself, waste minimization, including the consumables waste. I think these are some of the methodologies which can be used during the transportation. Of course, when the material has to be brought from the fabrication, the steel manufacturers to the site for the fabrication, we'll have to evaluate which transportation, whether by the sea or train, or the load is economical and the less carbon intensive. That has to be studied, and we need to have a look at it, and then we'll have to decide that. These are some of the methodologies during transportation, fabrication, and erection can be done. Finally, that I'll come to this circular economy, and look at this steel structure. I think the steel structure is truly compatible with the structural economy models, and because it is recyclable and it is fast constructable, and none of the steel, whether it's a stainless steel or a weathering steel or a normal steel, less strength steels, which we have been using, carbon steel, what we call it as carbon steel, and all these steels are recyclable, and it can be used once again. So from that point of view, I think the structural steel as a material is with the utmost compatible with the circular economy models. And here is one of the case. It's a very versatile and a very flexible material by virtue of its high strength to weight ratio and also the ductility which it has got. Basically, this is one of the examples where the bridge which was constructed using pre-stressed concrete technology, of course, at the state of the art at that particular point of time, has deteriorated over the period. The superstructure started sagging because of what we call it as a creep phenomena, long-term creep phenomena. And it is not because of the corrosion and all, as has been said in many forums. It is particularly because of the long-term creep phenomena. Also, the central hinge, which was in vogue at that particular point of time, and the sagging particular case, and always in a long span bridges, as I explained, that the foundations are more carbon intensive. Not only more carbon intensive, it is highly uneconomical to do the foundations in the river. Here's a particular case where the superstructure, concrete superstructure, is replaced with the steel truss superstructure, as you can see here. So it can be used for the prolonging the life of the existing structure itself, making the existing structure less carbon intensive. So the steel is a highly circular economical model oriented this one. When you are talking about the life cycle assessment of the bridges, whether it's economically or whether global warming wise or the social impact wise, what we are talking about, we have got four different boundaries, as you can see here. That's a product stage, that's a material production stage, that's the A1 stage, what we call it as. Then the bridge construction stage, again, it's the A1 stage. That's another boundary. Then the bridge use stage, that where the maintenance of the bridge has to take place, where like the expenditure takes place financially as well as the socially, and also global war in place, all during this fourth stage. Even the bridge demolition stage, which is possible for us to do the assessment, economical assessment, environmental assessment, as well as social impact assessment, as you can see here. Now, during the maintenance phase, or the operation phase, what we call it as, what normally done in the life cycle assessment is, say, for example, here, you can see here, this is around in 100 years. Suppose a bridge is designed for 100 years. That is a life which we designed the bridge for in Indian, as per the Indian codes. And if we design the bridge for 100 years, the surface of the deck has to be replaced in 25 years once and the 75 years once. This could be the maintenance regime which you can define is rehabilitation of the deck can take place after 50 years once a rehabilitation of the deck analysis or the life cycle assessment, and a new surface abutment, and say, for example, steam build production. It can be done on 25 years, we can specify 50 years and 75 years. And equipment used, cleaning of the expansion joints, I think it has to be continuously used, as you can see here. Only in 2050, that year it is not done. Otherwise, continuously it is required to be used. When you are using this equipment, normally there is the environment impact, social impact, as well as the economic impact. All assessment has to be done during the operation period, as you can see here. The bridge also normally is designed taking into consideration the average traffic study, average traffic details, as you can see here, in a day, how the traffic fluctuation on the bridge takes place. And over the period also, the traffic forecast has to be done. Accordingly, the number of lanes required for the bridge has been decided. And it has to be decided basically. And say, for example, if your forecast is saying that after 50 years, the bridge has to be widened, and in your life cycle assessment, that widening cost as well as the widening global warming potential also has to be calculated over here. And sometimes when the bridge is under the maintenance or the repair, we'll have to study the traffic pattern. The traffic congestion will take place. Because of the traffic congestion take place, there will be an impact, a social impact, environmental impact, as well as the economic impacts. That assessment has to be done. Say, for example, here the work is done over here. This is the approach speed. This is a deceleration zone. This is a queuing zone, as you can see here. Then the road traffic is constricted over here. Because of that, suddenly the acceleration takes place. This is a working zone. The average speed will be very less. Again, the acceleration takes place. And because of this sort of things, there could be an accident. Like if it is not properly done, the accident which took place recently when our Cyrus Mystery was traveling, it was said that it was not designed, the signages were not designed and it was not designed properly. That is why the accident takes place. All these things have to be calculated and assessed in the life cycle assessment cost, as well as the life cycle assessment of the carbon. In fact, I explained about this environmental effect, impact. Apart from this global warming or the carbon dioxide emission impact, under the environment impact assessment, many things have to be studied. But at this stage, I think it's enough for us to study the global warming thing. Of course, in the economic impact assessment, the initial cost, operation cost, end of the life cost has to be calculated. Social impact, it is the vehicle operation cost, driver delay cost, and the accident cost has to be calculated when you are doing the life cycle analysis, as you can see here. It is just some sort of a broad view on the life cycle assessment, how it can be done. A lot of research is going on all over the world, in fact, and we can take cues from there. In fact, the responsibility of giving a guideline on the life cycle assessment is with Dr. Harshavardhan Subbarao, He has been collecting a lot of information, and we'll have to come out with the life cycle assessment calculator for both the economic model as well as the global warming model. That is the carbon dioxide emission model for that matter. In conclusion, I would like to say that if you really look at the analysis which I showed here earlier, the embodied carbon of the steel which has been used in the bridges is around 963 million tons. Carbon dioxide equivalent being emitted to the environment. This 63 million tons carbon dioxide emission has to be brought to zero as committed by our Prime Minister by 2017. All of us have to be done. From the structural engineers, engineering fraternity or the civil engineering fraternity, I can assure that the design efficiency, circular economy, as well as transportation, fabrication, and the erection, it is possible for us to bring down this to the zero by 2070. But my worry is, like this, 70% of the embodied carbon is due to the embodied energy. When I say the embodied energy, as you can see here, 605 ton or 45 million ton carbon dioxide emission is due to the energy used in producing the steel. Basically, 162 million gigajoule energy is required to produce this steel. Unless this energy used during the manufacturing of the steel, by use of the renewable energy source, I think to bring this carbon footprint to the 2070 to zero, or achieving the carbon neutrality by zero, is a very hard task. My suggestion is, one way of going about it, all these steel making plants can have the captive renewable source power plant itself, like that they can use. It could be a solar power plant, it could be a wind energy power plant, it could be any biomass power plant. I think they should plan it. Once they replace it, I think CCUS is working very well, in my opinion. I think they are converting many of this carbon captured carbon into this ethanol, which is going to be mixed with the petrol which is being used right now. And similarly, that can be used in some other places also. That industry is working very well. Only way to go about is, we have to insist upon our steel manufacturers to have their captive power plant to provide that energy, so that they get this energy from the renewable energy sources. With this, Harsha, I've come to the end of my presentation. I'll be able to take the questions as you wish at any time. Thank you very much.